All right. So today we're going to continue talking about another statistical test. This one is called the chi-squared test. And there's actually two different versions of this that we'll look at. You will be doing a chi-squared test as part of your IA. So this will be something that, like, we got to be able to do. So there's two different versions of this test. There's the goodness of fit test and then the test for independence. This first set of slides, we're going to be looking at the goodness of fit test. I abbreviate that as GOF. So if we want to examine the distribution of a single variable in a population, the chi-squared goodness of fit test will allow us to determine if a given distribution fits with what was expected from the beginning. So what do we say? What do we mean by fits? So, like, suppose, like you are you have a manufacturing process, right? And the specification on your product is, like something, like say you're manufacturing like, like a little fun-sized bag of chips. And you want, and say that, in the manufacturing process, you're supposed to get like 22 chips in a bag or something. That's the goal. Say you want to look at how well your manufacturing people are following protocols, and you sample from that some bags of chips off the assembly line and count how many chips are in there to see if that kind of fits with what you expect or not. Does that kind of make sense? Or if, like, we think that, like, 50% of students should be boys and 50% should be girls, you can sample a class population and see if that fits, right? Or like 12% of people have blue eyes and 13% have green eyes and like 62% have brown eyes, or whatever. And you can kind of test the same thing, right? So the other way that we can use a chi-squared test is we can use it to test for independence. So that allows us to compare two different variables and see if there is a association or relationship between the two variables. So are these two things related? It's starting to sound like what you're doing for your IA, right? Where you're picking two variables that you think have a cause and effect relationship. Okay. So let's look at an example. So the Mars brand makes milk chocolate candies. According to the Consumer Affairs Department, the color distribution of its M&M milk chocolate candies is as follows. The 13% should be brown and red, 14% yellow, 16% green, 20% orange, and 14% blue. The table here, what we did is we sampled a bag of M&Ms and counted up how many of each color we got. So what I'm going to do now is I'm going to calculate the percent of each color that I got for blue, orange, green, yellow, red, and brown. just by taking like 9 and dividing by 60. So like I got 15% of my candies were blue. And I'm going to do that then for each. Or I could do that again for each, or I could just do it for one. Now the given for me before said that 24% of M&Ms are supposed to be blue. So that doesn't seem like it matches, right? Because we saw that, well, in this bag, we only got 15% that were blue. So I'm going to set up a hypothesis, a one sample t-test to check this. And now I'd have to do that one at a time, one for each color, right? If I wanted to do this with a t-test. Alternatively, we can kind of do this all at once using the chi-squared test. So our null hypothesis here would be that the color distribution that was stated is correct, right? That the color proportions matched what was given to us by the company. The alternative is that that color distribution is not correct. So essentially, if I did this symbolically, you know, the probability for blue is 24 and orange is 20 and blah, 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 blah. And the alternative is at least one of those is wrong. So to do a chi-squared test, we have to start by comparing our observed counts, that's what we counted from our pack of M&Ms, with the expected count. So what should I have gotten if the null hypothesis is true? Right, so that's the expected count. So let's calculate those. So if I know that 24% of my candies should have been blue, and I had 60 candies, I should have expected 14.4 blue M&Ms in my pack, right? Where I just took the expected probability times the total, and that should have been how many I would have expected to find in my bag. So I'll do that now for each of the colors. So again, these were the proportions that were given to me. 60 was the size of my sample. So in that 60 M&M sample, this is how many of each color I should have expected to have gotten. So I have now a two-way table where I have my color and I have what I counted in my bag, what I observed, versus what I've expected. Everybody's okay? Luca?
The 0.24, that's the probability of that?
Right, that was the 24% of M&M should be blue that was stated at the original.
How do we get that?
It would have been given to you. Like that was from like the M&M's company specifications of like that's what they're trying to do. Everybody's okay? So all those percentages would be something that's given to you. So we go ahead and do that. We have our observed and our expected. And now what we want to do is, okay, so here's a visual. Doesn't look like they're the same, right? Looks like there's some difference going on, but that's not good enough. What we'd like is like a numeric way of measuring, like how different from the expected really is what we found. And that's, to do that, we're going to be calculating this chi-squared statistic. So the formula for the chi-squared statistic is it's going to be the sum of the observed minus expected squared over expected. And we're going to do that for each observation, right? So we'll do that for blue, we'll do it for red, brown, yellow, and we'll add up all those differences. And that'll be our chi-squared statistic. So in this particular problem, we're going to do observed minus expected over expected. I'm sorry, observed minus expected squared over expected. And we'll do that for each of our colors. Look at how fancy color-coded that is. So when I add those all up, I get 10.180 approximately. Everybody's okay? So the way to think about that number now, that 10.18, is as a measure of the distance of the observed counts from the expected counts. Typically, large values for chi-squared is evidence against the null hypothesis, and small values are evidence for the null hypothesis. Or you could say large chi-squares are evidence in support of the alternative, and smalls are evidence in support of the null. Either way of saying that is fine. But the question now becomes, how big is big enough, right? Like 10.18, okay, is that a big number? Small number? I don't know, it's a number. We said big values. So the way we decide is we're going to think about much in the same way when we did the t-test. We looked at the area under the curve and talked about a probability. Same kind of idea here. So it's going to be a slightly different looking distribution, and the shape of the distribution depends on what are called the degrees of freedom. So for the goodness of fit test, the degrees of freedom is just the number of categories minus 1. So again, depending on how many degrees of freedom, your distribution is going to look a little bit differently. So the way that, for us, the calculator is going to find the probability will change because the shape of the distribution is different. Right? Like if I have 4 and up, that's going to be a different probability for the orange curve than it would be for the teal curve, right? So the shape of the curve matters a little bit. And the last thing we need to say before we're into like how to actually do this now is that just because you did a chi-square test doesn't mean it's a valid statistical test. There are 2 conditions that have to be met before we can assume the validity of our chi-square test. And this is important, right? Because you'll be doing a chi-square test and you'll have to verify the same thing for your IA. So essentially, the first one is that our sample that we're testing can't be too big. It has to be big enough, but not too big. And the second is that our expected counts have to be at least a certain size. So specifically, I guess we don't have it written out nicely. Specifically, your sample can't be more than 10% of the population. Well, for M&Ms, it's like 60 M&Ms, more than 10% of all the M&Ms in the world. Oh, clearly not, right? So we're good there. And the other is that the expected counts have to be bigger than 5. If we go back to the previous page, all of our expected counts meet that condition also. So we're good. This will be a valid chi-squared test. So much in the way with the t-test where we compared the p to alpha, the probability to our level of significance, we can do the same thing with a chi-squared test. So again, we got a small probability that is support for the null, and if the probability is big, it's support for the alternative. right? Is that right? Yeah, we'll say it again in a second. Okay, same idea. Or we can compare our chi-squared statistic that we calculated to a chi-squared critical value. Much in the same way we could compare t to t critical. We talked about that. Same idea here. But in order to get that t critical, we have to have a stated level of significance. So we can always compare p to alpha, or we could compare, chi-squared calculated to chi-squared critical. So if that chi-squared is bigger than the chi-squared critical, then we should reject the null, mean that's evidence in support of the alternative. And if the chi-squared is less than or equal, or the chi-squared calculated is less than or equal to chi-squared critical, that's evidence in support of the null. So like, here's an example of a distribution, a chi-squared distribution. Here's the area under the curve. That's our p-value. This is our chi-squared calculated value, the 10.18 from our M&M example, right? Because that's the spot where the x value, where we have that probability. So for 5 degrees of freedom, if I have a 15% level of significance, my chi-squared critical would be 10 or 8.12. For 10%, it would have been 9.24. For 5%, it's 1107. Notice that chi-squared calculated is less than chi-squared critical at the 5%, which is evidence in support of our null hypothesis, which is saying that we have good evidence in support of that the M&M stated distribution of colors is the correct distribution of colors. Even though, like when we drew the bar graph comparing the expected counts with the actual counts, the observed counts, they didn't look very similar. It's actually similar enough, statistically speaking. The alternative way to make a conclusion based on our chi-squared statistic is using the p-value, much in the same way that we did for the t-test. So again, if p is less than alpha, that's evidence for the alternative. And if p is greater than alpha, that's evidence for the null. Notice here that the relationship between p and alpha and chi-squared critical are opposites, right? For chi-squared critical, if chi-squared calculated was less than chi-squared critical, that was our support for the null. Here, if p, the one we calculate, is greater than the level of significance, that's actually support for the null. So it can be easy to get those flipped around.
Wait, chi-squared critical, like when you're using that alpha value? So we compare chi-squared calculated to chi-squared critical, or you compare p to alpha. And the chi-squared critical is coming from a level of significance. That's where that comes from. That would be something that would be stated in the problem. It would be like chi-squared critical at 5% is 15.2 or something. Like it would just tell you. Okay.
It's not something you'd ever have to find. It would just be listed. But much like the t-test, in order to give you the chi-squared critical, they'd also have to give you the level of significance. So you could always just compare p and alpha also, oh, here's my summary. So again, the two conditions that we need to have for a valid test is the randomness condition, so that our data comes from a well-designed random sample or a randomized experiment, and our sample can be no more than 10% of the entire population. The large counts condition is just that all of our expected counts are strictly greater than 5. Not greater than or equal to, it has to be strictly greater than 5. Okay. So first things first, the chi-square test works on counts, not probabilities. So like on that previous M&M's example, you don't want to compare like 24% with 9 out of 60. We're not comparing probabilities, we're comparing counts. And then when we check the large counts condition, make sure you're looking at the right count. We need the expected counts, not the observed. So 2 little things to watch out for. Okay, so to carry out the test, in summary, we're going to check the 2 conditions, the randomness condition and then the large counts condition. We'll then write our null and alternative hypothesis. The null is always going to be the stated distribution for the variable is in the population is correct, i.e. it's a good fit, or something to that effect. And the alternative is that it's not correct. Then we'll find the expected counts and calculate the chi-squared statistic using this formula, and then take that chi-squared value and compare it to the chi-squared critical. Or if we're using our calculator, compare the p-value to alpha. But you can't get the p-value without a calculator. Not for a student in this class. Okay? Okay. So let's do a examples. We're in chapter 13 there, genius. Let's minimize some of this stuff so it's not right there. All right. Don't worry, my random student caller is amongst the things that I lost, so I'm going to have to rewrite that code, which
darn it.
was a pain in the butt, but worked so nicely. All right. So let's run through a couple of these examples here. We'll need that. Okay. Jenny made a 6-sided die in her art class. That's a normal, Monopoly dice, right? Labeled each side 1 through 6 and rolled it 60 times to test if each side was equally likely to show up on top. Assuming that the die is fair, calculate the expected counts for each possible outcome and state the null and alternative hypotheses for the test as well. Okay. Who is going to tell me the, well, let's start with the null and alternative.
The null is that the dice is fair, and the alternative is that it isn't. Or that it's not that it's fair, that it's the outcome is equally possible.
Yes. Okay, so pretty good. So you'd want to say that. So your first statement is that each outcome is equally likely for the null is good. And then I would just say the same thing as the null, but I would add the word not. Yeah. That's good enough. Does that feel okay to you guys? All right, who can tell me the expected counts?
Well, we have to have like what she rolled.
Jax is correct. So we rolled the dice 60 times, right? If each is equally likely, there's a 1 in 6 chance of getting each of them. So there should be 10 1s, 10 2s, 10 3s, 10 4s, 10 5s, and 10 6s. Because 1 6 times 60 is 10. And each of them have 1/6. Everybody feel good there? Okay. Now, for Jenny's die in example 1, the following table contains the results of the 60 rolls of her die along with the expected counts. Use this table above to calculate the chi-squared statistic. Now, my suggestion for you guys is we're going to do this using a table on our calculator rather than like, thank you, Luca, it's for you. Rather than like grinding out all the data entry by hand. So I'm going to go stat edit. In L1, I'll go ahead and type in my observed. If you have your calculator with you and wish to follow along, not a terrible decision. Note that I'm not typing the 60 down there. Okay. So far, so good. Now what I'm going to do in L3, I'm going to move up to the title of L3, so it's highlighted, and I'm going to press enter. And then I'm going to do the calculation. I'm going to do observed minus expected, quantity squared, divided by expected. That's the formula. So my observed counts were in L1. My expected counts were in L2. And then I need that squared divided by my expected counts in L2 and press enter. So that's, now I just have to add each one of those up. The easiest way to do that is do stat calc one variable stats on L3 because the sigma x is the sum of those values in L3. So 3.4 should be my chi-squared statistic. Everybody feel okay there? To get the p-value from this, I can take the chi-squared CDF to do this, but let's not. Let's just show you how to do the goodness of fit test. So if I do stat and I go to tests, I'm going to scroll down till I find the chi-squared GOF test. There it is. I need my observed counts, which were in L1. I need my expected counts, which I put in L2. And I need my degrees of freedom. How did I calculate that again? It's the number of categories minus 1. So think about it this way. I have like a choice here. That's 1 degree of freedom. I have a choice there. 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 But by the time I've picked 5 things, there is no choice for the 6th spot, right? What goes there is the only number that hasn't been picked yet. So there's only 5 choices I can make in how to like order 6 things. Does that make sense to you guys? Because the last thing on the list is always just going to be, there's no choice anymore. You have to use that one. All right, and I'll hit calculate. And there's the same chi-squared value that we calculated with the table. And woo, look at that p-value. That's a big beefy boy right there. So I would compare this p-value to, or it says just calculate the p-value. Well, we did that, right? Now, that's a monster p, right? Regardless of any alpha we've been talking about, 5, 10, 15, this dwarfs any of those, right? What does it mean when p is greater than alpha? There it is. P greater than alpha is support for the null hypothesis. Okay, P greater than alpha is a support for the null hypothesis, which means that our dice is fair, right? It's not weighted to one side. Does that feel okay?
Which numbers are alpha again?
Well, it didn't state an alpha, but
You're just assuming.
well, look at the size of the P. Like, it almost doesn't matter what the alpha is, right? If we ever done a level of significance at like 65%, it's like, no, that's a crazy number. Like, that's such a big P, it almost doesn't even matter.
Oh, I thought that was a dot.
Yeah, that's 63%,
Oh.
right? Like, or 64%. Like, that's an incredibly big P. All right. Why don't you guys here try this one? And we'll go through it here in a second. So according to the 2000 census for all U.S. residents aged 60 and older, 19.1% are in their 20s, 21.5% in the 30s, 21.1% in the 40s, 15.5% in the 50s, 22.8% in the 60 and up. The table below shows the age distribution for a sample of 1,048 U.S. residents aged 20 and older. Members of the sample were chosen randomly, dialing landline telephone numbers. Okay, so before you start, we should do two things. Null and alternative hypothesis. Okay, what is the null? I would just say that the age distribution of U.S. residents 20 and up matches the known distribution. Or is correct. The known distribution for U.S. residents age 20 and up is correct. And the alternative is that it doesn't match or it's not correct, right? Make sure you say don't use the word it. I'm going to say it in this context because, we're just having a conversation here. But if you're writing on a piece of paper, you should spell out exactly what it means. Stay away from personal pronouns. Okay? So we have our null and alternative. Then let's calculate our expected counts. What is that flashing for? I don't know. You're dumb. Stop flashing. Actually, do that first. So we'll just put my observed in.
The last one. Oh. Is it-
So this is, I went and calculated my expected counts. So that was like 0.191 times 1048. And then 0.215 times 1048. So those are all there. Notice I kept the entire decimal. I want to use exact values there. So far, so good. And the way I did that easily, so I didn't have to do the calculation a bunch of times, I just did 1048 times, and then I put the probabilities in L3 and just let the calculator handle the repeated multiplication for me. So once I have that, I can check my two conditions, right? We did random dialing, and then 1048 is definitely less than 10% of the US population, right? US population, well, 1048 is 10% of about 10,000. There's a heck of a lot more people than 10,000 in the US, even ages 20 and up, right? It's got to be several hundred million. And then the expected counts are all way over 5. So we're good on our two conditions. So now I'll do my chi-squared test. Now, you probably want to show the work on how you would do that by hand. But when I actually calculate the number, I'm not doing it by hand. I'm using the calculator. So I used L1 and L2 for my expected. I had 1, 2, 3, 4, 5 categories. So I have 4 degrees of freedom. So the way I would write my work here on on my piece of paper, I'd say chi-squared equals 141 minus, and I think that number was 200.168 squared over 200.168 plus dot 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 plus 211 minus 238.944 squared over 238.944. And then I would just say equals, and I'd use my calculator to say it was approximately 48.2, rounded to 3 sig figs. I would say the P was, yes, sir.
So I like the whole test is like you want us to show it just like that, actually right on.
So if you're looking at like a test or whatever, this to me shows you knew what to do, right? If you write the whole thing out, that's fine. If you just want to give me like the first and the last because there's like annoyingly too many. Depend a little bit on the instruction on a test or quiz if I want all the work or just like do this. But if you give me that and you end up with the wrong number somehow, I can give you some partial because at least I know you're doing the right thing. You know what I mean? Okay. And our P is 869 times 10 to the negative 10. Ooh, doggy. That is teeny tiny. So that's evidence in support of, yeah. So evidence we had in support of the alternative that the observed age distribution does not match the known distribution. What do you guys think? Not bad? Not bad. All right, let's look at the other version of the chi-squared test then. This is the test for independence. So here we're going to be comparing two separate variables to see if they're related.
Wait, is goodness of fit test, is that the chi-squared test?
So that's also a different version of the chi-squared test. So goodness of fit is for one variable.
So
Where
there's
you-
3 versions of it?
Two versions of chi-squared, and we had a t-test last time.
But if we just did the chi-squared, on there it said there was goodness of fit or something, and there was independence.
Right.
Oh, is there just one?
So we've just done goodness of fit today so far.
Oh.
We've done a couple of examples of
So
it.
the ones we just did were goodness.
Yes.
Oh,
So that's where you have one sample and you're comparing against a known. For independence, you're going to be comparing two samples to see if they're related. All right. So this is the same slide we already saw. Blah, blah, blah. So we're trying to show that our two, that shouldn't say qualitative, that should be quantitative. Variables are independent of one another. So we start the same way. We write a null hypothesis, which can always be stated in the manner that like variable x and variable y are independent of one another. I need to see that word independent in your null hypothesis for the chi-square test for independence. Okay, so have to have that word independent. I'm not going to would not give you credit for something like not related, not correlated, not caused by. Has to be the word independent. Okay? The alternative is always can be stated in the same way. Variable x and variable y are dependent of one another. Again, if you don't have that word dependent there, it's not correct. And when I say variable x and variable y, you're going to fill in like what those two things actually would be. Like, bird beak size and bird weight or something, All right. So the basic idea is that we're just going to be looking to see how far away the two data sets are. So just like before, we'll calculate the chi-squared statistic and then compare it to the chi-squared critical. Blah, 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 blah. So let's look at an example here. So this is the number of hours a person sleeps and then their overall weighted GPA. So here is our data table. So we categorized our GPA into 3 categories: less than 3.5, 3.5 to 4, and more than 4. And our hours of sleep we categorized into 4 categories: less than 5 hours, 5 to less than 6, 6 to less than 7, and then more than 7 hours. And then this is the result from our survey. Everybody feel okay there? Okay. Now this table is our observed counts table. What we'll do next is make our expected counts table. So to do that, we're basically going to be looking at like finding the probabilities inside of here all is. It's going to be row total times column total divided by overall total, and that'll get you the expected count in each cell. It's basically just a probability calculation, but like, it doesn't matter. We haven't talked much about probability yet anyways. I'm just going to tell you the formula. And we do that for each cell. Blah, blah, blah. So row total times column total divided by overall total. That's going to give you the expected counts. So you'll make an expected counts table to go alongside your observed counts table. Everybody see that? So we have our observed, that's what our survey gave us. The expected counts, that's what we just calculated by doing row total times column total divided by overall total. Okay, and notice that I don't bother ever totaling up my observed or expected counts because those numbers don't mean anything for us. Okay. So next we'll go ahead and verify our two conditions for a chi-squared test. We said it was a random survey. It's 110 students. Well, there's way more than, 110 is 10% of 11,000. There's way more than 11,000 students in the world, so I think we're safe there. Our expected counts, the smallest one is 6, which is still bigger than 5, so we're in the clear there. Okay. So the formula to find our chi-squared statistic is still the exact same formula. It's observed minus expected squared divided by expected. Still the same formula as before. Now, we're going to have a lot more things to add up, but that's fine. Blah, blah, blah. Okay, whatever. So we add these all up. So if I calculate the chi-squared portion for each of these categories, that's the numbers I got. Notice that this one was 0 because I literally had a 9 for the expected, and I saw 9 students in that category, right? So notice our biggest contributor is this one because the expected count had the biggest difference from the observed count. They're the most far away. So that was like my biggest contributor to my chi-squared statistic, which was 12.6. Everybody feel okay? And again, the work, I would never write out all stinking like 12 of these little fractions. That's like just a big fat waste of my time. Do one or two, do a ... do the last one and write your equal sign and use the calculator to handle it. Okay, so we get 12.6. The question is that a big chi-squared or a small chi-squared? How would I compare this to? So we need some kind of level of significance based on our degrees of freedom. So again, the degrees of freedom, same idea as before, but this time we have a lot more choices to make because we have a whole box, like a table of values to fill in, right? So that's going to be the rows minus 1 times the columns minus 1. So in ours we had 3 rows and 4 columns. So we should have 2 times 3, or 6 degrees of freedom. Everybody's cool? NBD. Have to remember, though, that the degree of freedom formula is different between the two. All right. So again, what are we going to compare this stuff to? We need some kind of level of significance so we can generate a chi-squared critical or a alpha and then get a p-value out of our chi-squared number. So let's say that our level of significance is 5%. or I guess 10% is what we decided here. So we got a couple of degrees of freedom. We already talked about that. Blah, 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 blah. Look at this terrible looking graph I made. So, anyways. Blah, 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 blah. So, if chi-squared calculated is less than or equal to the chi-squared critical, we accept the null. That's evidence in support of the null. If chi-squared calculated is greater than chi-squared critical, that is support for the alternative. Or, if we calculate it, if we get a p-value, if p is greater than alpha, that's the equivalent of saying chi-squared calculated is less than chi-squared critical, then we have support for the null. And if the p-value is less than alpha, that means chi-squared calculated is greater than chi-squared critical, so we have support for the alternative. Yes, sir.
I'm still a little confused on which one is chi-squared calculated or chi-squared critical.
So chi-squared calculated is the one that we find. That's the number that we just, the 12.8 or whatever it was. Chi-squared critical is something that would be given to you in the problem instead of a level, or along with your level of significance to compare it to.
Yeah.
Basically, it's if I take my chi-squared curve and I fill in, like, if this is the chi-squared critical for 10%, I'd find 10% of the area under the curve, like the last 10%, and the x value that 10% piece starts at is my chi-squared critical. So if my chi-squared calculated is less than that, well, then that means its probability is bigger, right? That's for the null. If it was less than, it would be after it. So it means it has a smaller probability. That's support for the alternative. So they're really saying the same thing. Okay, so back to our example. Our chi-squared critical would have been, or would be given to us at 10.645. We note that chi-squared calculator is greater than chi-squared critical. So we have evidence in support of the alternative. Or we could also say that the p-value is less than the alpha. So I drew in what they would have looked like had we drawn them. Let's do the in-class examples. Again, if you have your calculator handy, I don't know why this thing keeps flashing at me. What do you want? I don't know. All right. So the administrators at Notre Dame Prep want to see if they are selling the correct food in the vending machines. They install 3 vending machines in the lower, middle, and upper divisions that each sell chips, Pop-Tarts, and gum. And they count the total sales of each type of food at the end of each week. So those are the totals that we found. State the null and alternative hypothesis for this chi-squared test. Who can do this? Luca.
I don't know.
So what would you call this variable? I would say the food in the vending machine
Is
independent of division of the school. Sounds perfect. And the alternative is that they are dependent. You'd want to say the two things, what the two things are, but yes. In a conversational setting, that is perfectly fine. What's the degrees of freedom we have here? The degrees of freedom is 4. 3 minus 1 times 3 minus 1. Make sure you don't count the total as a variable. Calculate the expected counts for the table. So, Mr. Kulik, is there a good way of doing this on my calculator, calculating the expected counts, or do I have to do it all by hand? Yeah, you can do it on your calculator. So let's take a look at this. So if I do stat, before I do that, I'm going to go and into the matrix menu. Into matrix A, I'm going to edit that. And I'm going to type in my observed counts table with no totals. You guys hear that terrible sound? That is the fan in the projector. That sounds like it's going to explode, right? Based on how my luck has gone this week, I think I'm probably about 1 day away from another technology breakdown. So I went ahead and entered in my observed counts table. Now I'll do stat tests. And I'm going to scroll down till I find the chi-squared test. So the independence test doesn't have GOF on it. Do I have to do that? I didn't think I had to. Let's just see what happens. Let me open that real quick. I thought I didn't have to do that, but in fairness, it's been a minute since I've... No, I did not. Great. So that is my chi-squared value and my P. And if I go back and I look at, say, matrix B now, and I look in there, it has my expected counts already done for me. The calculator did it. You don't actually have to do your expected counts by hand. You just do the chi-squared test and it'll do it for you. Woo, pretty nice.
You just plug in those numbers, right?
Yeah, without the totals.
Yeah. You don't have to do like the degree of freedom. You don't have to minus one. Like. take it away.
No, the calculator does it for me.
Oh. Cool.
It uses the dimension of the matrix to calculate the degrees of freedom for you. So you don't have to even give it to it. Yeah, pretty rad, right?
Okay.
So we have, yes, sir. Oh, yes. So that gave us everything we needed by doing that, right? And that p-value we found was 0.009, which is way less than alpha, which is evidence in support of the alternative. And then we do the same thing on the next page. What do you guys think here? Do you want to do the next one? No, yes, maybe. You guys are like dead to the world today. Luco's the only one talking to me. I need to.
After the world.
You feel dead to the world?
Yeah.
Okay. Well then, all right.